These notes are on the fundamental theorem of algebra, which has two pieces. First, given any polynomial where all of the exponents are positive and all of the coefficients are positive integers, and all of the coefficients and constants are constants, excuse me, there we go. The number of roots will be n. There will be n, including multiplicity. The other piece of the sort of fundamental theorem of algebra that's, I guess it's kind of a separate theorem, but it's related, is the remainder theorem, which says if a polynomial is divided by x minus a, where a is a constant, then the remainder is p of a. So we're going to look at a bunch of examples to try to make some sense of this. The first example, we are given a function, and we're asked if x equals 4 is a root. We're also asked if x equals 1 is a root. So we have two options here. One option is to divide f of x by x minus 4 and x minus 1. However, the remainder theorem makes our job here a lot easier. And it makes our job a lot easier because all I have to do is simply plug in 4 into my function. So 4 cubed is 64. Negative 13 times 4 is minus 52. Plus 12 gives me 24. So if you remember from division in elementary school, when we have a remainder, we don't have something that's equally divisible, that's going to be a perfect divisibility. So we would actually conclude here that x equals 4 is not a root of f of x. So now we're going to try again. Sorry, we had a little technical difficulty there. Now we're going to try again, but in this case with f of 1. So I have 1 cubed minus 13 times 1 plus 12, which gives me 1 minus 13 plus 12, which is 0. Which means that if I get a remainder of 0, that I can say x equals 1 is a root of f of x. Let's look at a second example. In our second example, we're given a slightly different situation. We are told that the roots with multiplicity are given, and we're asked to write the polynomial in expanded form. So for part A, I'm given 3 roots, but I'm told that one of them happens twice. I'm also told the leading coefficient. So we'll call this f of x. If this is one of my roots, I know one of my factors is x minus 2. If this is one of my roots, I know that one of my factors is x plus 3, but they tell me there are 2 of them. And if this is one of my roots, I know that one of my factors is x minus 8. And then the leading coefficient, I should have started with that. Let's go back and give it a little bit of space here. My leading coefficient here is going to be negative 2. So I'm going to start by multiplying the x minus 2 and the x minus 8. Multiplication can happen in any order. So I still have my negative 2 in the front. I have x squared minus 10x plus 16. I'm also at the same time going to multiply x plus 3 quantity squared, x squared plus 6x plus 9. I'm now in a position where I have to multiply by negative 2 and then multiply that answer by this. I'm actually going to leave the negative 2, and instead I'm going to multiply these two trinomials. So x squared times x squared, x to the 4th, x squared times 6x, 6x cubed, x squared times 9, 9x squared, then I'm going to do the negative 10. I have negative 10x cubed, negative 60x squared, negative 90x, then I'm going to do the 16, so I have plus 16x squared, plus 6 times, sorry, I lost my train of thought, 6 times 16, which is 96. So I have plus 96x, and then 16 times 9, which is 144. So plus 144. I'm going to combine my like terms here. So I've got x to the 4th plus, here's an x cubed, here's an x cubed, and actually it's a minus, so it's minus 4x cubed, minus 4x cubed. Here's an x squared, here's an x squared, here's an x squared. So I have 9, negative 60, and 16. So 9 and 16 is going to give me 25, but the negative 60, so that's going to give me negative 35. So I have negative 35x squared. My plain x's, I have a 90, negative 90, and a positive 96. That gives me a positive 6x. And then, of course, I have my 144. And my last step here is going to be distributing out the negative 2. So negative 2x to the 4th plus 8x cubed plus 70x squared minus 12x minus 288. My second example here, I am given the roots, I'm given the degree, and you'll notice here that I'm only given 3 roots, but the degree is 4. And that's because, going back to the previous notes, whenever I have a complex root, I also have its conjugate. So now I can say my roots are x minus 3, x minus 0. And now this comes the part that many students find tricky, which is that this says that x equals 1 plus 4i. But I need it to equal 0. That's what I've done to go from 3 to x minus 3. So I have to subtract 1 and subtract 4i. Oh, now I've gone into my space here. So we'll just write it here. X minus 1 minus 4i, which means this one gives me x minus 1 plus 4i. Multiplying the 2 in the front together is pretty straightforward because it's single distribution, because it's the x. So I have x squared minus 3x. Multiplying 2 complex roots here is going to be a little bit more complicated, but it's not as big of a deal as it sounds. So just like this is basically multiplying 2 trinomials, which we did above. So x squared minus x plus 4xi minus x plus 1 minus 4i minus 4xi. Sorry, I have to continue down here. I know this is always a little sloppy when that happens. And I lost my train of thought. Okay, so then plus 4i and minus 16i squared. I still have my x squared minus 3x in the front. Combining like terms, I have just an x squared. I have plain x's here, 2 of them, minus 2x. My positive 4xi and my negative 4xi cancel. My positive 4i and my negative 4i cancel. I still have a plus 1 and I still have a minus 16i squared. But remember from Math 2 that negative 16i squared is actually negative 16 times negative 1. So this gives me x squared minus 2x plus 16. And now I distribute one last time. So x squared times x squared times negative 2x, x squared times 16, 3x cubed plus 6x squared minus 48, yes, 48x. Combining my like terms, x to the 4th minus 5x cubed plus 22x squared minus 48x. You'll notice that in this case I lined up my multiplication so that when I went to combine my like terms, they were actually on top of each other. And that's another strategy that you might find to be very helpful. The next example, we're asked to find the roots. And at first, we look at this and we're like, I can't factor this. However, we actually can. It turns out that I can do something called factor by grouping. So I look at the first two terms and I can factor out an x squared, which leaves me x plus 1. I look at my second two terms and I can factor out a 3, which leaves me 3 times x plus 1. And then you'll notice that I have two x plus 1's here, which means I can factor that out from both and actually end up with x plus 1 times x squared minus 3. And so now I'm in a position where I can find my roots because I know that x plus 1 equals 0, which means I have x equals negative 1, and x squared plus 3 equals 0, which is x squared equals negative 3, which is plus or minus the square root of negative 3, which is plus or minus I square root of 3. So we would say that our roots are negative 1, and just because it's kind of nice to write it so that we can actually really see that there are 3 of them here, I'm separating out the plus minus, the positive, and then its complex conjugate. Our last example is set up so that we can't factor. We can't factor by grouping here. We can't factor using some of the other methods that we've used. But they give me a hint, and that hint is that one of the roots is 4. So that means that if I were to factor this, I would have x minus 4 with something. I need to find that something. Now, one would really hope that all I would have to do is plug in 4 to g of x. But all that is going to do is verify that 4 is a root. It's going to give me the remainder. I need to get the other piece of that division. So I'm actually going to have to take the time to divide my polynomial by x minus 4. And I want to double check one thing before I start, which is that I have x's to all the powers starting at the largest. So 3, 2, 1, 0. Otherwise, I'd have to stick in a 0 in there just to make sure that I was getting, that I was lining up all of my multiplication correctly. So the first question I need to ask is x times what gives me x cubed, and that would be x squared. So x squared times x squared times negative 4. And here comes the part that, in my experience, students most often make mistakes, which is that if you remember with long division, once you got the pieces so that this canceled, it canceled because you actually subtracted, meaning you actually changed the signs. So now this cancels, which means I'm left with negative x squared. And just like in long division, I bring down my next term. I have to ask myself, what times x gives me negative x squared? That would be negative x. So negative x squared plus 4x. Again, the whole point of this is to get the leading term to cancel. So remember that when we did this back in elementary school, we always subtracted, which means to change our signs. Move down the next term. Again, what times x gives me negative 6x, negative 6. So I have negative 6x plus 24. And I subtract, and lo and behold, I get 0. Which I expected since they told me 4 was a root. In fact, if I didn't get 0, I would have to assume either that they made a mistake or that I've made a mistake somewhere in my math. So now I can rewrite g of x as x minus 4 times x squared minus x minus 6. If I multiplied this out, I'd get the original function. That's what this process does. It breaks down the original function into multiplication, into factors. So now I have x minus 4, and luckily for us, this factors. It's x minus 3, x plus 2, which now means I can say that my roots are 4, 3, and -2.